to have a voltage gain of 1. So you will say, what is it good for if voltage gain is 1? The thing is, this amplifier has a very high input impedance, much higher input impedance, and its output impedance, RL, when it looks back towards the emitter, is very, very low. So it makes the output of that amplifier like an ideal voltage source, input of amplifier as a high input impedance amplifier. But voltage gain, unfortunately, is low. It's 1. Just under 1. Slightly below 1. I will show it in a minute. So where do we use them? Usually when you have a high gain, is obtained from the CE, common emitter amplifier. So you obtain your high gain from a CE, but when you look towards the CE amplifiers, you see collector resistance, RC, which is usually a high resistance, 2K, 3K or so. But if you feed the output of the CE to the input of a CC, and you connect the load on the emitter side of the CE, you will see a low output impedance from the emitter side. It doesn't impart any gain to the whole scenario. The gain comes from the CE, but it allows you to couple low impedances, low load resistances to the amplifier set without reducing voltage gain. So the trouble with the CE was this. If you remember, we had a voltage gain, unloaded voltage gain, right? We had an unloaded voltage gain, which was voltage gain, GM times RC, excluding RL. Once you connect the load resistor, like 100 ohm, and RC is a 2 kilo ohm, the gain drops by 20 times factor because it combines, the 100 ohm combines parallel with RC. It's a gain killer for the CE. But if you post this amplifier in between, it overcomes that problem. It's a buffer. It's basically a buffer that buffers a low impedance interacting with the collector resistance of the CE. So the CE amplifier keeps delivering its high gain, while the CC amplifier protects the loading of the CE amplifier and keeps that gain to a high level. It doesn't give any gain. Gain is 1 only, but that's not what we want it for. We want it for its property of buffering. Once I start analyzing, I'll show you that. So about the DC analysis. The DC analysis of this stage is completely identical to what you had in the past, except you calculate, estimate IB, you design R1 and R2 accordingly to make the current in there at least 10 times of the current in the base. Then you set your Q point, and RL connects via a capacitor to the circuit. So when you're doing DC analysis, you need to know what is IC, all the DC values, VC quiescent and IC quiescent. There is no need to know RC. RC doesn't exist, it's 0. So the DC load line, that is relationship between IC and the VCE, is defined by this red curve here. This is called the DC load line. But when the signal comes in, the load line for that stage will change along the black line, which the slope would be 1 plus beta over beta is considered like 1, RE parallel RL. So this will be the 1 over RE parallel RL will be our dynamic emitter resistance. So the signal will play along the black line once the signals start coming in. So follow the same direction criterion as the CE for determining the all the DC values. Choose VE so that VC quiescent, which is defined by VCC minus VE, will yield the desired Q point with respect to the AC load line. What is the desired point with respect to the AC load line? If you can keep the Q in the middle of the black load line, you're a winner, because the swing will be maximized. The output positive swing is this chunk. Negative swing will be that one. And we can calculate the AC quantities. So let's go to the next page and see what is the AC quantities there. Small signal model. Okay, here it comes. So this shows you how to calculate the N value, which is pretty much like before, and the P value, which is RE, RC parallel RE, times the IC quiescent. Small signal model. Here is your small signal model. There, completely. So we start from the source. Let me just draw that model here. We had V of S, R of S, R of S, and then we have the capacitor. This is the actual circuit. R1 and R2, then transistor straight to the supply, emitter to the RE for biasing purpose, C1 and C2. This is the RL, and that's the output voltage VO. Okay, so let us start with the building of the small signal equivalence. That's the VI. In other words, voltage of battery. It could be a division of Vs, or you can simply apply directly an ideal voltage, so AC sourcing here, and drive the circuit. So how does the AC model work? Here, start with Vs, which is this one. It's that source. That's the Rs coming all the way to here. This is X of C1, which is shorted. Then you have R1, R2 going to ground. R1, that is not changing, so it's considered signal ground, doesn't have any signal on it. This is true ground, R2. Then you are here at the transistor, that's the base. This is the R pi, that's the emitter, that's the collector. GM times VBE is the internal current source, or beta times IB. IB is the current in this line. Excuse me. And then you have RE. Oh, this RO is for transistor in case if you happen to have dynamic collector to emitter resistance, you can incorporate from here to the supply, which means it's ground. So RO will appear there. In other words, RO appears to be parallel with RE. But usually, we don't account for that. So it's RE. Now, this is X of C2, which is short. It's this capacitor. Finally, ending with the RL. Now, you can analyze the AC performance. First of all, input impedance. Input impedance is defined as VI divided by II. And that is equal to R1 parallel R2 parallel with RB. This lowercase rb, which is defined here, RB, always RBs are equal to R pi plus 1 plus beta multiplied by RE parallel RL. So let me see Did I include RL or not? RB is not included. Okay, even better. So without the RL included, it's equal to that times RE. However, if RL was included, if RL was connected, substitute RE parallel with RL. So this figure would change to, this quantity would change to RE parallel with RL. That's simple. If RL was included, it will show up in the basic resistance equation. Now, the resistance RB is defined as, this is the VI divided by IB, flowing into the IB. This is the IB. Lowercase IB, which is the current in the previous one. It's here. It is this IB, the red one over there. So VI divided by that IB will be nothing but R pi plus 1 plus beta times RE, if alone. If not, accompanied with RL, RE parallel to RL. Then what is the total input impedance viewed in this direction? Here. So RI defined as VI over II. So what is II? II is this one. It's different from IB. II includes R2 and R1 as well. It would be simply R1 parallel R2 parallel with RB, which is classic formula, and it's that formula. So this will form the total input impedance of the common emitter amplifier stage. Now, about the voltage gain. So to calculate the voltage gain, we go to here. To calculate the voltage gain, you need to compute voltage across the here, which is the current IE multiplied by the resistance RE, or if RL was there, RE parallel with RL. So here is the outgoing voltage at exactly where this cursor is pointing, right there. Outgoing voltage VO is equal to 1 plus beta times IB, which we have the value for IB, which is equal to that times RE. Now IB is equal to VI over R pi, 1 plus beta times RE. So if you substitute IB into this equation, then VO over VI, which is known as AV, will turn out to be 1 plus beta times RE over R pi 1 plus beta times RE. However, in case if this is included, it's already parallel, all you need to do is alter that term into RE parallel with RL. That's what you have to do. RE parallel with RL. If accompanied with Now, this is our voltage gain formula, which completely tells you, if you know how much voltage you have here, which we can easily figure it out, because once you know the input impedance, you can calculate from that source what is the voltage over there. And then knowing the VI and knowing this equation, you can transfer and calculate the voltage at the final destination. All right, one significant thing about this equation. If 1 plus beta, this quantity, which is same as that quantity, if that dominates over R pi, happens to be much, much greater than R pi, look what will happen. Delete R pi in comparison. The two terms will cancel from top and bottom. You'll get 1 in theory. But because we have some R pi anyway, the denominator is going to be tagged higher than the numerator. So this ratio is going to be tagged lower than 1, like 0.99, 0.98, etc. So voltage transfer from here into here is almost like 1. So if the common emitter amplifier, preceding common emitter amplifier, was sending a signal with a relatively high resistance of Rs, it would completely transfer that voltage from that point into the output with a voltage gain of 1. But it will block RL loading the source resistance. In a minute, I will solve a problem in this one. So that is basically all you need to know about the equations of it. Gain is almost like 1. Let's see what else is left. Yep, so this is the gain formula. And AVI. This is the formula in terms of GM. So if you want to change beta into GM, you're welcome. All you have to do is, for beta, substitute R pi times GM in that equation. It will lead into this one. So 5 and 6 are literally the same thing. Input impedance, as I said, R1, R2 with RB. And what else is there? Output resistance, yeah. Output resistance viewed in this direction is very, very low. Here, exceptionally low. R out. External to RL. R out external to RL is equal to RE in parallel with RS parallel R1 parallel R2. Combine them, add R pi, divide by 1 plus beta. So this is the output impedance. Actually, this part, this resistance that you see is the resistance viewed in this direction. And what I have accounted for with the RE is when you move, put it external to the RL. So remember, in the direction of the emitter, always, it's a classic formula. Output impedance in the direction of the emitter is background resistance here, parallel with R1, parallel with R2. It's like Thevenizing to the left, from the base to the left. So these three appear to be parallel. Then they appear to be series with R pi. And then you divide by 1 plus beta. So that's the way to utilize it. It's a classic formula. I proved it in 2 different ways. So get used to using it, how to apply into problem solving. So this is the resistance. This will be the resistance if you look in the direction of XX, but when parallel with RE, it will be in the direction looking towards this side of the capacitor, external to the R. It's a very low resistance because beta is usually a very high quantity. Theoretically, if beta goes into infinity, this will be 0. 0 with RE, parallel with will be 0. So you'll get ideally 0 output impedance. So you have got 0 output impedance. So when you change RL, it's not going to drop the voltage because it will retain the same voltage. It has a very low output impedance. Typically, this quantity can be like 10 ohm, 20 ohm, something of that size. So if you put a 300 ohm resistor here, that's a 10 ohm, you won't see any significant drop in the voltage. It will almost stay the same. But if you take that 100 ohm resistor or 300 ohm resistor and you try to couple it to a CE amplifier, oh, it will kill RC because 300 ohm with a 3 kilo ohm RC, it will reduce the voltage gain down to nothing. So this guy is protected, it's a buffer. Now let me just give you ideas about the capacitors. So how do you design the capacitors? This one here, X of C1 has to be much, much less than Rs plus Ri. So Ri, we know the value already. Plug it there, calculate C1. C2 has to be much, much less than RL plus Rout, which is that formula here, which is this one. This formula. And practically, because Rout is very, very small compared to RL, delete this, X of C2 has to be much, much less than the resistance you're incorporating here. For example, if RL is 100 ohm, make sure at the minimum frequency, reactance of that is only 10 ohm, minus J 10 ohm, versus that 100. It's very easy to design the values. So, let me see what else is there, 4 out of 4. I think this is done. I'm going to put an example. Probably it's, yeah, there is an example in here. We've got a 30K, 1K, and RL, 12 volts, 1 volt peak to peak, 2 kilo ohm over here. Let us calculate, it says VO without RL. So it says, what is VO without this resistance? VO with RL equal to 200 ohm. Find C2, minimum is 80 hertz. Find a suitable C1. What is the MPP available? The output under the 200 ohm condition when RL is 200 ohm. What is the MPP without RL? So, what is the MPP available at the output under the 200 ohm condition? RL equal to, and then without that, what would be MPP? Okay, pretty straightforward problem. We only need to solve it. So let me get rid of all of this. This goes off. I can even leave that here. We've got a source. This is 1 volt peak to peak. 1 volt peak to peak over there. It has a resistance of Rs equal to 2 kilo ohm. 2 kilo ohm. And we have a load. RL equal to 200 ohm. 200 ohm. And this is our VO. Number one. direct coupling. RL with source. This will be the result of direct coupling. If you directly, with a capacitor or something, you couple that load resistance into this source, which produces 1 volt peak to peak, this will be the outcome. 200 ohm, 2000 ohm, plus 200 ohm, times 1 volt peak to peak. This will be approximately equal to about 0.09, I think, very small amount. Use my calculator. This will be 200. That would be 0.09 of a volt. Of a volt peak to peak. Here, you put 1000 millivolt peak to peak in here from the source. If this load is a 200 ohm, you try to couple it, you will lose your voltage to this amount, 90 millivolt peak to peak. That is a substantial amount of reduction compared to the fullest you could have gotten. If you invent something that is a buffer standing in between, it will transfer the node voltage from here to there, even with a gain of 1, without increasing, but it will avoid interaction of that resistance with this 2K. Then you can capture almost all of that 1 volt across your load resistor, maximizing the power in that load resistor. Okay, so what is that buffer? That buffer is nothing but the emitter follower, as an example in here. We're going to calculate it. So our circuit is this, using CC amplifier. So your CC amplifier consists of, here, it was a 12 volt power supply, 30K and a 30K. With the C2 coupling to the RL equal to 200 ohm. This is the C1, and this is the RS equal to 2K, and that is the original voltage source, VS, equal to 1 volt peak to peak. Okay. So this is our original circuit, and this RE is equal to 1 kilo. RE equal to 1 kilo. And this is the R1 and R2. All right, proceeding with the calculation, of course, this is the reference ground, 0 volt. Okay, now we want to calculate. First, DC analysis. Because we need to determine the parameters. For the DC analysis, this node is the VI. Okay. For the DC analysis, you strip the circuit from the capacitors. This is the IB, uppercase B, means it's a DC. Then we try to Thevenize here. Thevenize. DC. DC Thevenization. ETH is equal to R1 over R1 plus R2 times the VCC, that's the VCC, is equal to 30 over 30 plus 30 times 12 is equal to 6 volt. RTH here is equal to 30K parallel 30K 15 kilo ohm. That's the RTH. So IB is equal to ETH minus 0.7, the voltage drop, DC voltage drop for the transistors, divided by RTH plus 1 plus beta multiplied by RE. This RL doesn't show because we are doing DC analysis. Capacitor is open, obviously. So we need to get a beta value. Did I suggest a beta here? No. Take beta equal, here, 150. So beta is 150. Beta is 150. That's typical. So we put the values over there. ETH 6 minus 0.7. RTH is 15K plus 151 multiplied by 1. So this is 5.3 volt divided by, that is 166 kilo. So that's equal to 5.3 divided by 166, about 32 microamp. It's 31.9, take it 32 microamp. Therefore IC is going to be 150 times 32 microamp. Times it by 150, 4.79, about let's call it 79, 4.79 milliamp. So GM for the transistor is equal to IC over VT, and we are also taking VT like normal, 25 millivolt. So it's 4.79 divided by milliamp over 25 millivolt. That divided by 25 is equal to 0.19 about S Siemens, and therefore R pi is beta over GM is equal to 150 over 0.19. So we'll flip this, times it by 150. That's 783 ohms. I just absorbed all those roundings in my calculator, so it's like almost exact answer. Okay, 783 ohm is the R pi. That's all I need from section from the DC analysis. And also one more thing that I need is to see where it is in the IC VCE plane. So IC, and this is the VCE. We need to calculate what is VCE. That's the voltage VE. V of the E is equal to IC, IE times RE, approximately equal to IC times RE, is equal to 4.79 volt. That's our VE, 4.79, roughly. You know, we take IC and IE almost the same. 4.79 volt. V of the C, collector voltage, check here, same as supply voltage, right? Gentlemen, please note, if I had an RC in here, which is silly to have it there if you're not using it, then I would even hamper that voltage to a lower level. The swing would be even smaller. So it is not to my advantage to have any resistance over there. The higher the better, because we can get a larger VC quiescent, therefore a larger swing at the emitter. So that's why we don't put the RC there, putting there doing what? So VC is the VCC automatically, which is 12. So you can say VC quiescent is equal to 12 minus 4.79 is equal to 12 minus 4.79, 7.2 volt. 7.2 of a volt. So it's here, 7.2 volt. This is the VCE quiescent. Equal to that. That's the VCE. This is the IC. And the current is, IC and IE are almost equal, 1.79 milliamp. Here, 4.79 milliamp. This is the IC quiescent. Okay. The next thing is going to be along the AC load line, which we will determine what that is. Okay, so now we need to determine the AC values. So what is RI? AC parameters. Number one, what is RI? Which is VI over II. This is the VI, and our I is here. So ratio of that voltage to the current will define an input impedance, which we can determine what will be the value of VI arriving at that node from the original one. Here it's 1, but I'm going to get less. So the formula for VI over RI is called RI. It's known as the RI, input impedance of stage. Okay, so it says initially, what do we do? Without RL. First, without RL. It's trying to calculate it without RL. With RL equal to infinity, without. So when it says without, in the formulas, parameter becomes infinity. Resistors become infinity. So without RL, here is the RI. RI is R1 parallel R2 parallel RB, where RB is equal to R pi plus R pi plus 1 plus beta times RE. See, RE, not RE parallel RL. If it was with RL, that would add to it in form of parallel. So here is our RB. RB is equal to R pi 0.783 K. This is going to be very, very small, plus 151 multiplied by 1. So this is approximately equal to, let me write it exact, okay? Equal to 151.783 K. it will be equal to that. Then I will substitute up there. Therefore, Ri is equal to 30K parallel 30K parallel to 151, 151.783 kilo is equal to here 151.783 Yes. 13.65 kilo ohm. Okay, there you are. Input impedance of that amplifier without the RL or with a very, very large RL, like 100 kilo, right, is equal to 13 kilo. Note one thing. You see this 151 is way higher than those resistors. Actually, these two resistors, other than the biasing that is necessary, are menace in here. I would like to have a very high input impedance. So this guy was providing it already, 151 of its own. We are losing just because of these two biasing resistors. They're too low. And we cannot make it too high. There's no way of doing it because the current in here has to be at least 10 times of the current at the base, or else your bias won't be quite stable. So when it comes to application, it pays off to combine this base with the collector of a preceding stage to bias that stage automatically, and we could avoid these two resistors. I will show you with another example later. You have a question?
Quick clarification. What does RI stand for again?
Input impedance. That's the ratio of, Ri is the ratio of voltage to the current that flows through that node towards the circuit, which is equivalent to a resistor hanging from here to ground. The name is Ri. Name is Ri. So this is what is the Vi. You've got Vs, 1 volt peak to peak. You have 2 kilo ohm, this is your Rs. This node is the Vi, which is the net input voltage here under the coupling of the stage with the source. And then you've got an Ri hanging from here to ground, which is equal to 13.65 kilo ohm. And then the question is, what is Vi? How much voltage from that 1 volt in here is reaching this corner? See how much voltage from here is arriving at that point? Because this input is loading it, it's drawing current. It's drawing current from that source. So it has got to drop the voltage. That's what we are determining. Once I know this voltage, I can quickly get that voltage for you. The quickest, 1-to-1, same voltage comes out. But we can detail it. Maybe it's 2% less, but we can find out. So here is your Vi. Vi is equal to 13.65 over 2K plus 13.65 multiplied by 1 volt peak to peak. That's your Vs. Here is your answer. Vi is going to be 13.65 divided by 15.65, 0.8872 volts of peak to peak. So this is the voltage that is going to reach here. And I promise you, when I calculate the voltage in here via the AV, voltage gain formula for the stage, that voltage is going to be exactly identical to this voltage. Okay? So that means if you put a load resistor in here, it can transfer 0.8 volt, 0.87 volt. That means 87% of that voltage into the final destination. Can deliver that via this arrangement. Whereas without it, this would be the fatal case. Only 9% of the source arrives at the destination. So that 1 volt is reduced to 90 millivolts here. That's the role of the buffer. This guy is playing a buffer. Now we are not done yet. So what is VO over VI? VO over the VI without RL. This is with RL equal to infinity or without RL. It's the same thing. Okay, so the voltage gain would be 1 plus beta times RE over R pi plus 1 plus beta times RA. Notice that RL is infinity. So this is the ratio of VO over VI. That is equal to 151 kilo ohm, or 151 at the top, divided by 0.78 plus 151 is equal to 0.99 something. 0.78 plus 151 equal invert times 151. 0.99994. This is the voltage transfer from here all the way to here with infinite resistance, with RL equal to infinity. Then, here is the answer, therefore. VO over VI, which is 0.872, is equal to 0.994. Therefore, VO with RL equal to infinity is going to be that times of 0.872. 0.86, actually 87 volt peak to peak. Okay. With very large resistance placed in here, like a 10 kilo ohm, 100 kilo ohm, practically in the final destination you can capture 87% of the signal from that source. This source could be a source of intelligence, source of information, a sensor or something. So you get a good signal delivered to the load. Now, the next step is, what happens if you change and you plug in an RL of 200 ohm in here? Then what will be the voltage in here? What would be the VI? So I'm going to repeat the problem again. But this time it's going to be with RL. So let's erase this part. We don't need that anymore. Now, with RL equal to, how much we said here? RL equal to 200 ohm. We've got to recalculate. Not the DC, absolutely not. DC is set because it doesn't affect. Capacitor doesn't show. Just we need to know what is the RB. RB will change. RB this time will be equal to R1 parallel R2 parallel to R pi plus 1 plus beta multiplied by RE parallel with RL. I should put this into brackets like that. All right, so here it comes. 30K, 30K, RPI, same thing, 0.783, because it doesn't change. 151 multiplied by 1K parallel with 0.2K. 0.2K. Note this is the RL. This is the RE. So we need to figure this out. 30 parallel 30 parallel with 1 times 0.2 divided by 1.2. 1166 times 151, 25 kilo plus 0.7. Right. This turns into about 26 kilo. Considerably reduced. So such a low value of the load resistance will considerably reduce the value of RI from 151 into 25. As a result, we will lose quite a lot of the signal. So let's see how much it is. Therefore, RB, this is the, I'm sorry, this is not RB, this is the RI. This is the RI, this part is RB, sorry. This chunk is the RB. In other words, this part is your RB. Okay. So, RI is equal to 30 invert at 30 invert at 26 invert again, 9.5 kilo. So we reduced considerably from 13K to 9.5. From 13K to 9.5. Which is not that much dramatic, but it did anyway. Now we need to calculate what happens to the VI, because according to this model, this has changed to 9.5K with RL equal to 200 ohm. This is with RL equal to infinity yet. For very large resistance. So, here is the VI equal to 9.5 over 2K plus 9.5, these are K's, multiply by 1 will be the peak, there you are. 9.5 divided by 11.5. 0.826 volt peak to peak. Not bad, still we have 82% of that signal. And I tell you, offhand I can tell you, we're going to get almost the same thing at the final end, towards the 200 ohm, when I calculate the new AV, the loaded AV. So this is my input. Now AV, this is with 200 ohm RL is equal to 1 plus beta RE parallel RL divided by R pi plus 1 beta RE times parallel with RL. This is our voltage gain. So RE used to be 1K, now parallels with the 200 goes down to about 200 ohm, but we need to calculate. So this is equal to 151 multiplied by RE parallel RL. It's this guy here, 1K parallel with 0.2. It is 0.2 divided by 1.2. 0.16. 0.166 kilo ohm over R pi, which is the same, 0.783 kilo ohm, this is the R pi, plus 151 times 0.166. Point times 151 equals, this is equal to 25.16 over 0.783 plus 25.16, and the AV that we have here, which is nothing but VO over VI, that is with RL, is equal to that ratio. If you work it out, plus 0.783, flip that, times 0.96. This is 0.97, 0.97. Okay. Not bad. You see, your gain was 1 in that case, almost 0.994. Now your gain is a little less. Not much, 0.97 from 0.99. So what is then the final output? Final output, you have it. It's the VO over the VI. So VO over VI is equal to 0.97 here. VI, okay. So VO over, let me write the final number here. 0.826, 0.826, that's the VI, times 0.97. Okay, there is final answer. VO is equal to 0.97 multiplied by 0.826. 0.80. Okay, this concludes the whole thing. There. So, what are we learning from here? If you connect if you connect a very high resistance, like 100 kilo, very high, and you apply a 1 volt peak to peak over there, the amount of the voltage that will appear across that 100 kilo or very large resistance would be equal to 0.87 volt peak to peak. 0.87 volt peak to peak, right? With infinite resistance RL. Now, if you reduce your RL from infinity open to 200 ohm, how much we are going to get? I'm going to get 0.80 volt peak to peak. Do you see the percentage of drop in the voltage? From 0.87 RL equal to 200 ohm. This drops to 0.8 volt peak to peak. Look how much the voltage dropped. It's not much. It's about 0.07. It is 0.07 divided by 0.87. 8%. So the output voltage will drop only by 8%. You couldn't get that signal, 0.8 volt peak to peak, into 200 ohm. This demonstration showed that, you know, the earlier one. The one that we had with a directly coupled, you know. It was only 90 millivolt. You got 90 millivolt, 0.1 volt peak, as opposed to 0.8 volt peak to peak. So that circuit did its job, basically, which buffered it. You can also demonstrate what is the output resistance viewed in this direction, viewed in that direction. I bet it's going to be awfully small, something like maybe 20 ohm, 30 ohm, something like that order. It's a very, very small output impedance. That's why, you know, the 200 was not much of a load if you have a 20 ohm output impedance. It's likely to drop like 10% or 20%. So this is the demonstration. Now, how do you determine the capacitor size? A good point in here. All right, again, with or without, it affects very little. Let's say without. On this side, you have, looking that way, you have a RS, which is a 2 kilo ohm. Looking towards the input, you have an input impedance, which is equal to Ri, 13 kilo ohm. So for C1, on this side, you have Rs equal to 2 kilo ohm. On this side, you have Ri, which is equal to, let me go for the lower one. Ri equal to, we calculated here. The one that was a lower one. Oh, here. Ri was 9.5 kilo ohm here, 9.5 K. This is with RL. And X of C1 has to be much, much less than 2K in series with 9.5K. Okay? Therefore, C1 translates to 10 times 2 pi 80 hertz, because F minimum is 80 hertz. 2 pi times 80 hertz times almost like 11,500 ohm. 2K combined with 9.5 makes 11,500 ohm. That is going to be the size of the appropriate capacitance. So that turns to be 11500 times 80 hertz times 2 times pi times it by 10, 1.7 microfarad. It makes sense. 1.7 microfarad capacitor will do the job. In the lab, don't try to find 1.7 microfarad. It's not a must. We want to make sure above 80 hertz it's functional. So go get the nearest high one, the highest to the number you are calculating. Next standard is 2.2 microfarad. So put a 2.2 microfarad. If your frequency is 80 hertz or above, this will function the way it is supposed to. About the C2, which is very easy if you use a smart assumption. Just write it down and it will be accepted. Impedance, looking this way, is very low because we said transistors have a low output impedance at the emitter. But looking this way, it's the RL. So this capacitor has to be much, much smaller than the 200 ohm. So C2 comes out here. This is the E, very low, very low. This is the R out. Capacitor C2 is there. And here is RL, which is 200 ohm. So in this case, your C2 has to be C2 equal to 10 to pi 80 hertz times 200 ohm. Here is C2. It will be a little larger than that one, maybe 10 times larger. So 200 ohm times 80 hertz times 2 times 3.14 equal invert times that. 99 microfarad. Call it 100 microfarad. There it is. 100 microfarad will take care of that. It will, if the frequency is as low as 80 hertz, this will be minus 20 J at 80 hertz, which is much, much smaller than that. And yet that causes only 1% error between here and here. It's not complete short, but 1% off. But if the frequency goes higher, because these guys are used for minimum to a maximum frequency, 80 going all the way to the 20 kilohertz audio frequencies, right? And 20, at 1 kilohertz, it's dead short, basically. This capacitor is dead short circuit. So that is the purpose of CC amplifiers. And then, you know, next time when we come to the class, I will take a practical situation. I'll take a CE, cascaded with the CE, and we will analyze the performance of it. Its voltage gain, its power gain, you will see it will go up dramatically, the power gain. Voltage gain, power gain, etc., etc. Okay? So, about Wednesday, as I said, your question is on the CE amplifier. Variation of the CE amplifier. Any combination. It will be 1 hour test. It will have a DC analysis part and then an AC analysis part, just the way that I'm doing it in here. DC analysis, make sure you carry out your DC analysis part accurately and double check. Because you will make me happy if you do that. Because if you, all of you should come if you follow the procedure to the same result. And then there will be, if there is a mistake in the second part, which is AC analysis, at least you've got full credit on the DC analysis, right? You get full credit, like 50% of the whole thing is in the first part. And then it is easier to track if you make a mistake in the AC part. Once you have the DC analysis right, it's much, much easier. Otherwise, it will combine, you know, together. The first one will add to the. It's a hell trying to, you know, grade that situation. Sometimes it happens, not every time. So that will be it. And then bring one cheat sheet with you, single-sided cheat sheet.
Is it gonna cascading or just single amplifier?
Is what?
Is it gonna have cascading amplifier?
Cascade amplifier as well. There are CCEs, but it will be CE cascades. So I have done all the variation for you in the class. I'm try to get the best grade you can in test number 1. Yes.
How many questions do you have for that?
Usually 2 parts. One is DC analysis, the second is AC analysis. Yeah, that's how it goes. 50-50. No. Okay. CE. So the topic for today is not in your exam. Today's topic is not the exam.